Has anybody ever done writing chemical equations, balancing chemical equations, that kind of thing? Have experience with that? No, maybe a little bit.
High school.
In high school, maybe. Okay. Well, we'll talk about it here. A chemical equation is a way of writing, expressing on paper what happens when some chemicals react with each other and make something else. You've probably seen something like it before. We're just going to be a little bit more careful about how we write things and some of the formalities of what we write exactly. So a chemical equation might look something like this. H2 with a G plus O2, G, arrow, H2O, G. Some of those things you probably know what they mean. Other things maybe not. So the chemical formulas, we've been dealing with those. Those tell us what kinds of things are reacting. The things over on the left are the things that we start with. So that's what we're calling the reactants. Sometimes reagents. Sometimes just starting materials. Things you start with. And then the other side of the arrow we call the product. So we mix those two things on the left to make the thing on the right. Now that's not always how it works. In some reactions we'll see arrows going both ways, meaning that the reaction can go this way, these things turning into that, and also this way with this thing turning into those. So some reactions will be reversible. We'll see those as well. And then the arrow just means tells us about what's happening, what's becoming what. The other thing that we should know about here are these little letters after the formula. Anybody know what that refers to? Yeah, in this case, that's gas. So in general, that's going to be the state of the reagent or the product, state of the chemical in this particular context. So note that water can have, as with anything else, can be gas, liquid, solid. So depending on how the reaction is done, what the temperature is, what the conditions are, that can change. The states that we'll usually use in these reactions are ones that you can probably guess. G for gas, L for liquid, S for solid, and then there's one more that is not really a state but is useful in terms of reactions, and that is AQ. AQ stands for aqueous, which means, yeah, dissolved in water. So we'll see one of those four. You may not know which one to use when you're writing down an equation. And I don't just mean like you, like any of us. We don't necessarily know what that state is until we've actually done the reaction. So if it says, write an equation for this process and you're given some chemicals, it's not going to be assumed that you'll know which state to use. But when you're seeing a reaction that's written down, usually that will be included to give you that information. All right, there's one other piece of this reaction that's missing. Anybody know what it is?
An arrow.
What?
The arrow.
The arrow's there.
Oh.
The what?
One. There is two O, but here's one O.
Yeah, so there's some issues with some numbers of things here. One thing I think is helpful is to look at what this looks like from a molecule standpoint, like what the actual molecules look like, and then see what's going on. So hydrogen molecule is just two hydrogen atoms connected together with a covalent bond. An oxygen molecule is two oxygen atoms connected with a double bond. And then water is something like this. So this is a problem because in the way that we've drawn this, it seems as though one oxygen atom is simply lost in this reaction. But do you all see how there are 2 hydrogens on the left and 2 on the right, but then 2 oxygens on the left and only 1 on the right? That's not okay. Why is that not okay?
There are no stability.
Yeah, but why? What's wrong with that? Yep. Well, that's true. We will have to balance it. But what is it about, like, if you actually think about the materials, the physical things, what is wrong with losing one in the course of your reaction? Yeah. It violates something called the law of conservation of mass. That in a chemical reaction, mass can't be created or destroyed. You can't simply do chemistry and create more mass. And you can't do chemistry and destroy mass. You can't destroy atoms in a chemical reaction. We will talk later about nuclear reactions where that happens, but in a chemical reaction, we don't destroy matter. So that's the problem. So that means we have to do something to deal with that. Now, can we say, okay, well then instead of H2O, we make H2O2? Does that work? What do you think? Shaking some heads. Why doesn't that work? It doesn't work. You're right. But why doesn't it work? What's wrong with that? It does balance.
Maybe because of charges, because we have here 2, 2, and here we're gonna go 4.
Yeah, that's part of it. That when we change the subscript numbers, those little numbers on the bottom, we're changing the identity of the chemical, the identity of the compound. Does anybody know what H2O2 is? Yeah, hydrogen peroxide. Is that the same as water? No, not the same as water. Don't drink it. It's not, you can put it on your wounds if you get cut or something and they will help clean it up, but you don't want to drink it. It's obviously a different chemical, very reactive. So by changing that number, we've created something totally different, and that's not okay. So what do we do instead? How do we fix this issue of balancing the mass without changing the numbers of the atoms in the compounds? It's really a question of a ratio. This not balancing, what that really tells us is that this isn't the correct ratio. One hydrogen atom does not react with one oxygen atom. They have to react in a different ratio. So take a look at this. If I instead say, let's react these in a 2-to-1 ratio, and then form 2 water molecules at the end, I haven't changed the identities or the ratios or the numbers in the compounds. I've just changed the ratios, but now you can see everything actually matches up. See that? There's 4 hydrogen atoms on the left and 4 on the right. 2 oxygen on the left and 2 on the right. So this tells us that every oxygen molecule must react with 2 hydrogen molecules, not just 1. That they have to react in a 1-to-2 ratio, and that then 2 molecules of water will be formed. And the way we express that in the equation is to put the number 2 in front of the compound like that. And that tells us 2 molecules of hydrogen are needed for every 1 of oxygen. And similarly over here, 2 molecules of water are formed. All right. So that means that every time we write down a chemical equation, we have to check for the atoms and make sure that it's balanced, that there's the same atoms on the left as on the right. And if not, then we have to adjust the ratios to make sure that that is true. So let's look at how to do that in kind of a systematic way to make sure that we always get that right. Take a look at this reaction. And just for practice, for fun, what's the name of that first compound?
D.
I want to look it up on the periodic table. Do you have a name for that one? Close.
Iron chloride.
The SE is selenium, so that's selenide. Close. Close. It's going to be iron 3 selenide. Iron 3 selenide. Because each selenide is -2. It's in the same column with S and O. And there's 3 of them, so that's a -6 overall, which means each iron has to be +3. So that's iron 3. So iron 3 selenide. What about the next one? HCl. Yeah, hydrochloric acid. Hydrochloric acid. If it were HCl gas, it would be hydrogen chloride. But because when it's in solution, we call that hydrochloric acid. And what about the FeCl3? Yeah, iron 3 chloride. Yep. And then the last one should really be called dihydrogen sulfide, but we call it just hydrogen sulfide for some reason. So that one's covalent. All right, anyway, if we want to see if this equation is balanced, let's say we wrote this thing down, and now we want to make sure to have a balanced equation. This is the way I do it. If you've been taught to do it a different way, or if you like a different way, that's fine. The way I do it is first to count up how many of each atom are on each side. So we've got on the left 2 iron, 3 selenium, 1 hydrogen, and 1 Cl. And then on the right, we've got 1 iron. Whoops, that's not going to work. I think this is supposed to be sulfur. So that would be iron 3 sulfide. Sorry. I wonder if I don't know how to get that right. Anyway, 1 sulfur, 2 hydrogen, and 3 chlorine. This gives us a nice way to quickly look and see which ones are out of balance. In this case, they're all out of balance. All of the atoms have different numbers on each side. So we start with one of them, and we add a coefficient, that number out in front, to bring them into balance. So which one do you want to start with? Does it matter? Yeah, we'll start with Fe. In this reaction, it doesn't matter. We are going to see some where it does matter. What you want to look for is if there's one atom that exists in multiple different compounds on the same side, you want to leave that one till last because it's too hard to balance otherwise. But in this case, every atom is just in one compound on each side, so it doesn't matter where we start. So we can start with Fe. All right, so we've got 2 on the left and 1 on the right. So how do we bring those into balance? No, not exactly. We need to put a 2 here. And then, this is the important part, count up the new numbers. So now that we've put the 2 there in front, that means 2 of the whole FeCl3 units. So now we have 2 irons on this side, and we have 6 chlorides. You see how that number changes those things? All right, so we balance the iron. Where do you want to go next? The what? The Cl? Yeah, since we changed CL, we might as well jump to that one next. And then, like I said, it doesn't really matter, but that's fine. So now we have 6 CL on the right, just 1 on the left. So how do we bring those into balance? Yeah, we're going to need 6 HCl. And that changes this one to 6 and this one to 6. And probably the number one mistake I see in these, or at least one of the top mistakes, is when you put down one of those numbers, one of those coefficients, forgetting to change every other atom that gets changed by that number. So like it's easy to put the 6 there and change the 6 on your CL, but forget to change the H. And then you get confused when you go back to it later. All right, so now we changed the H, so let's balance the H's. We've got 6 on the left and 2 on the right. How do we make 6 on the right so that they're balanced? How can we get 6 H's on the right? Right, well, we're going to be dealing with this H2S, so we want to put a 3 there, because then there's 3 of those, and each one has 2, so that's 6 total. And that's going to give us 6 of those and 3 of these. And now we check our numbers, and everything is balanced. So we would say that's now a balanced equation. The nice thing about these is if you can count, you can always be pretty sure whether or not you're right, whether the equation is balanced or not. Just check, make sure everything has the right numbers on both sides, and then it's balanced. If they don't have the same numbers on both sides, it's not balanced. And this one worked out pretty nicely for us, but sometimes there's some trial and error involved, where you try something and it doesn't work, and then you have to go back and look again. So let's look at one that has that effect. The reaction for combustion of butane. Butane's a fuel, hydrocarbon used in lighters, that kind of thing. And when it combusts, it reacts with oxygen gas, forming carbon dioxide gas and water vapor. Again, I would start just getting a count of all the atoms that we have. So we've got 4C, 10H, 2O over on this side. This side's got 1C, 2H, and 3O. Remember that you're dealing with the entire side of the reaction when you're doing this. So like on the right, it's CO2 and H2O. Both of those oxygens count in the total oxygens on that side. This is one of those examples where it does actually matter where you start. If you started trying to balance oxygen first, you're going to run into trouble because there's oxygen is in both molecules on this side. So you don't know, like, okay, do I put more on this or more of this one? It's not clear. So you got to leave that till the end when you see a situation like that. Otherwise, it doesn't matter. We can start with C or we can start with H. Any preferences? C? All right. So let's bring those C's into balance. What do we do there? Yeah, we're going to put the 4 right here. And then, again, recalculate those numbers. So we now have 4 carbons, and instead of 3 oxygen, 11. 4 times 2 is 8. Or whoops, not 11, 9. 4 times 2 is 8, and 1 more is 9. Oh, I got 11. Okay, so then we can look, remember we're going to leave the oxygen till last. So let's take a look at the hydrogen. 10 on the left and 2 on the right. What do we put here to bring those into balance? 5, right? Because 5 times 2 is 10. So there's 10. Okay, so those are balanced. So how do we balance the oxygen? We've got 9 on the right and 2 on the left. what do we put in front of that O2 to balance that?
You don't have 9 on the right anymore.
Oh, good question. Yeah, good point. Yes. So that's why you got to remember to do the thing that I was just saying that you should remember to do that I then forgot to do. So now we no longer have 9 on the right. We have 13, right? 8 plus 5. Thanks. See, so it's easy to forget that. Okay, so now what do we do? How can we balance the oxygens? Yeah.
Would it be 14?
I don't think so, because 4 times 2 is 8, and then there's 5, and 8 plus 5 is 13. Yeah. Does anybody see a problem? What's the problem? Yeah, we've got an odd number on the right, 13, but on the left we can only balance in multiples of 2. So if we put 6 O2, that would give us 12. If we put 7 O2, that would give us 14. So we're stuck. Anybody have a clever solution to this problem? Yeah, but you can't have half a molecule. So what are you going to do? What? Add it somewhere else? Just one? That would kind of make for a different compound or a different reaction, right? Is there any way we can keep everything the same, but just change the ratios and get it to work? So there is a solution to this. When you run into this problem, and it happens, you need to double everything. Because like you said, we should really put 6.5 in there. But if we doubled everything, then that would end up being 13, and that would be okay. So let's double all the numbers that are already there and leave the oxygen alone and go from there. So instead of 1 of these, we're going to have 2 of these. Instead of 4 of these, we'll have 8. And instead of 5, we'll have 10. And let's correct those totals. So that's 8, 20, 8, 20. All the other stuff should stay in balance because we haven't changed the ratios. We've just doubled everything. And so now on the right, we have 26 oxygen instead of 13. And 26 is a multiple of 2. So now that works. And we can say, all right, we'll put 13 there. And that should work. Does everybody see that trick? Yeah.
I understand how we got the 4 and the 10, but how do we get the 9? We got lost there.
The 9.
The 9 by the 30. How do we get that?
The 9 by the 30. Oh, this one?
Yeah.
That was a mistake because I added wrong.
So it's supposed to be 13?
Yeah.
How do we get the 13?
When this was a 4,
Right.
so that's 8 from here.
Okay.
And then this was a 5, so 5 from here. And 8 plus 5 is 13.
Okay.
Yeah. The 9 was a mistake. That wasn't supposed to be there. All right. So now you can try one. Sodium phosphate reacts with magnesium chloride to form magnesium phosphate and sodium chloride. So this is often how you'll see these kinds of things written. It's a description of a reaction, and then you need to write a balanced equation for that description. Sodium phosphate reacts with magnesium chloride to form magnesium phosphate and sodium chloride. First question then is, which go on which side? So how do we know what goes on the left or what goes on the right? Any thoughts for this particular one?
Sodium phosphate, magnesium chloride.
Yeah, how did you know that?
This really reacts with.
Right, so reacts with kind of says these things react together, and that tells you those are the starting materials, the reactants. And then the other key phrase here is to form. So they're saying those things make these other things. So that means sodium phosphate and magnesium chloride will be on the left, magnesium phosphate and sodium chloride are on the right. So see if you can write a balanced equation for that reaction. If you don't have a periodic table with you, sodium is Na, magnesium is Mg, chloride is Cl, and phosphate is a polyatomic ion that you should know from the list. So as you probably figured out, part of the difficulty of problems like this is that you have to first come up with the correct formulas for the ions, for the compounds, before you can actually balance the equation. So you have to make sure your compounds are correct first. So I will write down the compounds if you haven't gotten there yet, and then at least you can have a chance to try to balance it. So there are the compounds. I didn't put the states in there because we don't always know that. In this case, it wasn't specified. But those are the correct compounds. Now, if you got any of those ratios off, like if you said Na2PO4 or NaPO4 instead of Na3PO4, that's going to affect the balancing and throw everything else off as well. Same with all these other ones. So make sure that you're still working on building compounds, ionic compounds from names, so you can do that correctly when we start writing reactions about it. We'll keep working at it. I'm going to balance it also here. Right. So there you go, a balanced equation. One other thing I did here that you may notice, I need another page here a second. Just a little bit. In balancing here, instead of individually going P and O, I kept that PO4 phosphate ion together. That's not something that you have to do. It would also work if you do P and O, but it makes it a little easier because we can see in this reaction that this isn't changed, that the PO4 stays together from reactants to products. So anything that doesn't change, it simplifies what you're doing if you just keep it together. This is especially nice when we get to, if you have an equation that has, let's say, PO4 and SO4. So then everything has oxygens in it, so your oxygen numbers get all crazy. But if you keep the PO4 together and the SO4 together, assuming they don't break apart in the reaction, that can make things a lot easier. All right. Let's try another one. potassium sulfide reacts with lead 2 nitrate to form potassium nitrate and lead 2 sulfide. Potassium sulfide reacts with lead 2 nitrate to form potassium nitrate and lead 2 sulfide. keep working. I'm going to put the compounds up here, but if you haven't gotten them yet, just keep your head down so you can work on your own. If after you're checking this, if you're checking your compounds, see where you went wrong and see if you can determine for yourself why one of the compounds ended up wrong. Did you get a charge wrong? Did you balance the charges wrong? Was it the wrong symbol? What was it that caused your problem in getting those compounds down properly? Luckily, once you get the formulas down, this one's pretty simple to balance. All right, any questions about this one before we move on? Okay. The last thing we're going to do for today is talk about the types of chemical reactions. This will come up in lab on Wednesday. There's lots of ways to categorize chemical reactions, and various disciplines have their own way of doing it. We're going to focus on this very general classification. The use of this classification is that it will help us predict reactions. If we know that a reaction belongs to a certain group, we can kind of figure out what the products are going to be. And you'll work with this a little bit in lab on Wednesday. You'll do a reaction from each of these 4 groups and kind of look at what happens and how we can figure out what those products are going to be. So here are the types. I'll give you the name, the general idea of how it works, and then a specific example or two. First type is called combination, or sometimes composition. And this is 2 reactants coming together to form one. So something like A plus B becomes AB. An example of that would be the first reaction we looked at today. H2 and O2 form H2O. It doesn't mean that you simply stick the reagents together. We're not making H2O2, but a reagent of the first type and a reagent of the second type come together to form another one. The reaction that we're going to do of this type next week on Wednesday is this one, where solid magnesium is combusted in oxygen gas to form solid magnesium oxide. Again, you have to look at the individual compounds to figure out this, the product here. You don't just stick the Mg to the O2 and say MgO2. We have to say, okay, we've got Mg, we've got O. What is the compound that's made of Mg and O? And then we use our normal skills and we say, okay, O is 2- and Mg is 2+. so we put them together in a 1-to-1 ratio. So that's combination reaction or composition reaction. Second, we have the opposite. A decomposition reaction, so a reaction where something decomposes. And that's of the form exactly the opposite of what we just did. So you start with just one thing, and that one thing breaks apart into two things, sometimes more than that. The one we're going to do next week is a solid calcium carbonate. When it's heated, decomposes into calcium oxide and carbon dioxide gas. Decomposition reactions are really hard to predict because unless you have some experience with them, you don't necessarily know how it's going to break apart. Is the Ca going to go by itself, or is the O going to go with this? So you can't really usually predict those in the way that you might some of these other ones. And the last two categories are called the replacement reactions. And these are the easiest to predict. So we're going to look at two varieties of replacement, single replacement and double replacement. Single replacement looks like this. Some reactant on its own reacts with something that has two parts. One of those two parts goes with the first one, and the other one's stuck by itself. Hence the single replacement. The A has replaced B as C's partner. These are usually ionic type reactions, so that the ions can switch places. And one that we're going to do on Wednesday is this one. Solid zinc metal reacts with HCl, hydrochloric acid, to form zinc chloride and hydrogen gas. Notice here, again, the form is followed, but the quantities have to be readjusted based on what we know about the chemistry. So on the left, we have zinc, which is our A, and HCl, which is BC. One of those two things is going to go with the zinc. If we were to predict this reaction, we could say, well, I think the Cl is going to go with the zinc, because we know metals make positive ions. And it's unlikely that hydrogen will go with that metal. It's more likely that chloride will, because we know chloride is a negative ion. So we make a new compound of zinc and chloride. But the ratio note is different. It's 1 zinc to 2 chloride, because zinc is a +2 ion there. And then the hydrogen is all by itself. But we know that hydrogen molecules actually are made up of 2 atoms connected in a molecule, not just H by itself. So that's how we would know to write H2, that indicates a hydrogen molecule. So that's a single replacement reaction. And then the other category is called double replacement. As you might expect, this has 2 reagents, each having 2 parts, and they switch partners. Cations and anions. Cations switch anions, anions switch cations. So something like that, where they switch partners. Here's an example. And I'm just going to write the reactants here, and then we're going to talk about how we can predict the products. We have a reaction here of two aqueous ionic compounds, barium chloride and sodium sulfate. So then when these two react, we can identify that this is a double replacement reaction because it's two ionic compounds reacting, each of which has two parts, a cation and an anion. So we can switch the anions and the cations and find the products. So we would expect in the product that the Cl would go with the Na, right, cations and anions, and the barium goes with the sulfate. So cations and anions switch places. Now we still have to come up with new compounds for those. So what is the compound between sodium and chloride? What does that formula look like? NaCl, yeah. And what would the compound between barium and sulfate look like? Just BaSO4, right? Barium is +2, sulfate is -2, so they react in a 1-to-1 ratio. So we would have BaSO4. The reason these reactions happen often is that one of these products is something called a precipitate. Now you saw precipitates in lab yesterday when we did some of those tests. It's when the liquid kind of gets cloudy or when a solid kind of drops to the bottom. We did a few weeks ago also. In this case, the barium sulfate is actually an insoluble solid, meaning that when barium chloride and sodium sulfate, these two soluble ionic compounds react, they form this insoluble barium sulfate, which drops out of solution, kind of gets cloudy or falls to the bottom of the beaker. And that's what we call a precipitate. That solid that's formed in the reaction and then settles down to the bottom. Is this reaction balanced? It's not, as it is. It's actually kind of a simple one to balance. We just need to put a 2 here. Okay. I forgot to load it up. Let's pull up the book and take a look at some examples of these types of problems. Is that big enough? Can you read that? Kind of. Identify the type of reaction, combination, decomposition, single replacement, double replacement, or combustion, which is not one of the, none of these reactions are combustion. We'll talk about that one later. So a compound breaks apart into its elements. What do you think that would be considered? Yeah, that's decomposition. It's breaking apart. What about copper and bromine reacting to form copper bromide? Copper and bromine form copper bromide, copper 2 bromide. What? Combination, right. You've got two elements combining to form another one. Can you write an equation for that?
is plus B.
Yeah, but I mean for that specific one, for B. It should look something like this. Copper, metal, which is just copper by itself. Bromine is actually Br2. Everything in that last column, along with O, N, and H, take a double. And then copper 2 bromide, CuBr2. And that's balanced as is. So that's an example of a combination reaction. What about iron sulfite breaking down to iron oxide and sulfur dioxide? Yeah, that would be decomposition. We won't write an equation for that one because we don't talk about sulfite. And then D, a silver ion from AgNO3 forms a solid with bromide ion from KBr. What would that represent? Yeah, that's a double replacement. You see the two ionic compounds here, AgNO3 and KBr, and then the silver forms a solid with bromide. So the Ag is going to go with the Br, and the K goes with the NO3. So that equation would look like this. AgNO3 plus KBr becomes AgBr plus KNO3. And all of those would be aqueous except the AgBr, which is a precipitate, solid precipitate. All right, we've got about 15 more minutes. Let's practice writing a couple more reactions. Oops. Or let's do some balancing. That's always good. All right, balance each of the following and identify the type of reaction. Well, let's work on this for about, I don't know, 8 minutes or so, and then we'll come back and look at them together. Flag me down if you're confused or stuck on one. All right, let's take a look at some of these. Any that you're having trouble with specifically you want to look at? First one? Okay. So let's set up how many of each thing are on each side. We've got 1 nitrogen on each side, 4 hydrogens on each side, and 1 chlorine on each side. So that's it. It's balanced. Doesn't need any more numbers. Right? All right. The next one down, one way you can do this, and I saw a couple of you starting to do this, if you don't like going through all of the atoms, you can go just looking at the equation like this and kind of pick the order you're going to do it in. So like if I see an equation like B, I might look at carbon first and say, all right, there's 4 C's on the left and 1 on the right. So I'm just going to put a 4 here. And not even count anything else, just do that. Then I know I have to save my oxygens until last in this kind of a reaction, so I'll look at the hydrogens next. I see 8 on the left and 2 on the right, so I need to put a 4 here to correct that. Then I am to the oxygens now, so on the right I have 8 plus 4 is 12, I think, yep. And so that means that I will need a 6 here to make 12 on the left. So this can sometimes be easier because you're just kind of bouncing back and forth, but you can also get into trouble this way. For C, I look at this and I see SB, which is antimony. I see that 1 of them on each side, so that's good. But then I see 2 chlorines on the left and 3 on the right. So how do I bring those into balance? Yeah, we need to ultimately have the same number of each. So we need 3 of these, and 2 of these. See how I did that? Now there's 6 chlorine on the left and 6 chlorine on the right. But now that's thrown off the antimony. So there's 2 on the right and 1 on the left. So we need to put 2 there to make sure we have those 2 there. And then last one, same thing. I could work with balancing the nitrogens first, so I'll do that. 2 means I need 2 there. And that means I have 6 iodine on the left. So I need 6 iodine on the right. So I'll put a 3 there. 3 times 2 is 6. This one, next one. So I look and see K and K, that's 1 and 1. Cl, 2 to 1. So I need 2 of those. That throws off the potassium, so I can correct that by putting a 2 over here. And I think that works now. All right, F. In this case, again, it doesn't really matter where you start, but I definitely want to keep the sulfates all together. So I'm not worried about sulfur and oxygen separately. I can see that sulfate stays together throughout the reaction, so that shouldn't be a problem. I've got 3 of those on the right and 1 on the left, so I'm going to want to put a 3 here to correct for that. That means 6 hydrogen on the left. I need 6 hydrogen on the right, so I put a 3 there. And then the only thing left unbalanced is the iron. There's 2 on the left, just 1 on the right, so I need to put a 2 there. And then finally, the last one, this is a big one, and here's one where you definitely want to keep the ions together. If you separate that out and look at oxygen and sulfur and hydrogen separately, it will still work. It will absolutely still work, but it'll be a little bit more confusing because of that. So it's better if we think of this as aluminum, sulfate, sodium, and hydroxide, and just have 4 things to balance. So I guess we can start with aluminum. We've got 2 on the left, 1 on the right, so we need to put a 2 here. For hydroxides, that's going to give us 6 on the right and just 1 on the left. So that needs to have a 6 hydroxides there. That's 6 sodium on the left to just 2 on the right. So we need a 3 there, so that 3 times 2 is 6, we can have 6 sodium. And those should all now be balanced. Questions? Concerns? Well, there's plenty of practice in the book for this kind of stuff, so have at it. Make sure you're comfortable with that. Usually this balancing stuff is a little easier for people than the naming stuff, so definitely keep focusing on those names, because as you saw, we're now going to bring those into the equations, and you're going to have to write equations from just the names, which means you have to write the formulas first and then put them in equations and balance the equations. So keep working on those. Make sure you know those polyatomic ions and that you can find the charges of various things that you can find. All right, thanks. I'll see you Tuesday. I'll be around tomorrow if anybody wants to come by. If you're having any trouble, I'll be around.